Right, so my aim in this talk is to give more explanation about the result that Dimitri mentioned just at the end of his talk, and hopefully have a more or less complete proof, modulo certain technical details, a complete proof of this result. So let me just remind you, hopefully everyone in this talk was also in Dimitri's talk, but just to refresh, the main objects we're interested in, the number of level set or excursion set components of some smooth stationary Gaussian field inside some large ball. And we know from the results of Nasaroff and Soden that these things have densities associated with them. So we have this convergence of the number divided by the volume of the ball. And this convergence happens almost surely and also in mean. So it's a strong notion of convergence. And this is true for every level and also for both of these quantities. So in other words, the law of large numbers statement is settled. We know that there is a law of large numbers, and we want to study second order results basically and see what we can do. So let me recap the result we're able to prove. So what we're able to prove is that actually the variance depends on the field. It's not always the same. For generic fields, in the sense Dimitri describes, so rather than talk about generic fields, I'll mainly just focus on the Bargmann-Fock field, which is this field with the Gaussian covariance kernel. So in particular, the correlations decay extremely quickly, and its spectral density is supported on the whole of plane. So it has spectral density because the spectral measure is the Fourier transform of the covariance. Since the covariance is a Gaussian, its spectral measure is also Gaussian. So in particular, it's positive at the origin. And what we prove is that for the Bargmann-Fock field, as long as you have this non-vanishing, non-critical points of your density function, then you have variance of order r squared. And for the random plane wave, you have density, as long as you have no critical point of your density function, and as long as you're not at zero, you have density, you have variance, sorry, order r cubed. So what I want to try and get across is that these orders are quite natural. This difference between r squared and r cubed, it comes out very naturally from the proof. We'll be able to understand where they come from. And we also expect these to be correct. It's a bit harder to see why they should be correct. And this is kind of work in progress. And the reason it's a difficult question is because we actually think it's probably not true for every level. So we think for Bargmann-Fock, it's going to be true for every level. It's always of order, always of linear order, the variance. But for random plane wave, we expect something strange, a bit strange to go on, mysterious to go on. At certain levels, we expect the variance to be of lower order. And that's by analogy with the variance of other geometric functionals, like the length of the level sets. There's anomalous levels at which the variance has lower order than at generic levels. So that's what makes this quite potentially quite complicated to get a tight bound. Okay, so let's turn to the proof of this result. Oh, no, let me mention actually something Manju asked as well. Can we go, because these conditions in this result are fairly implicit, right? These density functionals, they're defined via the convergence statement. So they're implicitly defined. We don't know how to compute them explicitly. We expect there's no explicit expressions for them. So therefore you might ask the question, is this result worth anything? Because can we ever check this kind of condition that the derivative is not zero? If we can never check this condition, then the result doesn't tell us anything. Happily, we can check the condition at certain levels to give explicit variance bounds. So let me just say explicitly what we can prove. So for the Bargmann-Fock field, for the level sets, well, we can prove it in the tails. So if the level is small enough or large enough, we can prove it. So it doesn't have to be too large. I mean, 1.38, this is compared to the standard deviation of the field is normalized to be 1. So it's within 1 or 2 standard deviations. So it's not really the tails, but yeah, only for sufficiently large L, we can prove this. Whereas for excursion sets, interestingly, we can prove it at 0. So we were quite happy to be able to prove this at the most interesting level, which is the nodal level. We can prove this bound at 0. We can't prove it if L is too small. There's a certain gap where we can no longer prove it. And then after a certain high enough level, we can prove it again. I'll try and explain towards the end how we prove these kind of results, if there's time. And for the random plane wave, similarly for the level sets, we need the level to be high enough or low enough. And for the excursion sets, we can prove it for all negative L. We can't prove anything for 0. We can prove it for small positive L, and then, so actually the gap for excursion sets of the random plane wave is quite small. You can see it's only a very small range of windows of levels where we can't prove the result. So the result is explicit in some slightly weak sense. Okay. So let me turn to the proof of this variance bound. So there's really 3 ideas I need to explain first, and then once we have these ideas in place, the proof will follow very simply. So let me state these ideas before studying them in detail. The first idea is very simple, and Dimitri's already mentioned it, is that these kind of global topological properties can be controlled or upper bounded by local observables. So as Dimitri said, you can always control level set components by critical points, and that's going to be a key to getting upper bounds anyway on global topological properties. I'll explain later more detail what I mean by this. This is just to give you an overview. The second idea is the idea that Gaussian fields can, in a sense, breathe. So you imagine, what I mean by that is your lungs kind of go up and down. We think of the fields and the field shifted by a level as being indistinguishable on some compact sets for levels small enough. So Gaussian fields have enough entropy within them to make level shifts kind of statistically indistinguishable. So again, I'll make this much more precise later, but that's the key, that certain small level shifts are statistically negligible because of the entropy inherent in the field. And lastly, we have a nice coupling argument. Actually, the basic argument is due to Chatterjee a couple of years ago, but there's a coupling way argument that allows you to deduce variance lower bounds at a fixed level by considering how that changes as the level varies. So Dimitri kind of mentioned this, that studying things at a fixed level is actually quite difficult. And you have to take the point of view that the level can vary in order to deduce some information at a fixed level. So what we'll be able to do is, by studying how the number of level sets changes, when the level changes, we deduce a variance bounds at the fixed level using a coupling argument. Okay, so that's the outline of the talk, and then we'll put it all together at the end to prove the result. So yeah, the first thing is, Dimitri's already covered this, so let me go quite quickly. So there's this basic idea from Morse theory. It's a caricature of Morse theory, really, that the number of level set components at any level is bound above by the number of critical points in the domain. You just have to imagine that inside every level set component, there has to be a local maximum somewhere, or local minimum somewhere. So clearly, critical points give an upper bound for the number of level set components. And that's useful because we have the Kac-Rice formula to compute the moments of the number of critical points. The number of critical points is a local quantity. It has an integral Kac-Rice formula. And in particular, we can say that the second moments of this quantity, just by bounding it by the number of critical points, is at most this double integral over the domain. So I think Dimitri only had Kac-Rice formulas for first moments. When you go to higher moments, the formulas get more complicated. But really, the upshot is that it's explicitly computable, at least as an order of R. So you can use some Gaussian methods to control these kind of Kac-Rice formulas. And the upshot is that the second moment of the number of level sets is of order R4. So this gives you a kind of trivial upper bound for the variance of the number of level sets or excursion sets to be R4. It's not interesting really, but what is interesting is doing the same thing in small height windows. So the previous result was just the number of level set components at a fixed level. But what we're really interested in is how things change when the level changes. So what we need is a variant of this result that works for two different levels. So the lemma's the following. If we take the number of level set components at two different levels, B and A, then by Morse theory, again, you can bound that by the number of critical points in the domain whose critical level, whose height lies in this window, AB. because as Dimitri explained, if you go from level A to level B, the topology only changes if you pass through a critical point. Otherwise, nothing changes. So the number of critical points tells you the number of times the topology changes, which is an upper bound for this change of number. And once again, this is useful because there's a Kac-Rice formula for the quantity on the right. Again, it's even more complicated. Now you integrate over the domain twice and over the level twice. But nevertheless, you can analyze it and you deduce some quantity for this change. So let's see what we have. Well, we see this R4 factor coming again. But if B and A are very close together, we really pick up an improvement of B minus A squared. Unless B minus A is too small, in which case the bound shifts to a different quantity. If B minus A is too large, then we get the previous result back. But the main result is this one on the left, that if B minus A is small, we get this improvement in this trivial, in a sense, second moment bound on the change in the number of levels using local quantities. Okay, feel free to interrupt me in the chat, or yeah, you can also interrupt me as well. Okay, so that's the first idea, that we have this local control over the change of a global topological property, and we get a second moment bound from that. Okay, so let's look at the second idea, that Gaussian fields can breathe, in a sense. So the idea is that we want to understand, if we restrict the Gaussian field to some compact domain, say B, the ball of radius r, how small epsilon should be so that the field and the field plus this constant epsilon are close in total variation distance. And hence any functional of them is also close. So the number of level sets is close. Any kind of geometric property is close. This is what we want to understand, but yeah, we have to be very cautious here, because in fact, this property is never true, literally. So it's never true that these fields are close in total variation distance. So why? How can we understand this? Well, I mean, you really have to go via this Hilbert space that Dimitri was talking about, because there's this nice result known as the Cameron-Martin theorem. You might be familiar with it from the theory of Brownian motion, say, that tells you exactly when you can make shifts to a Gaussian process whilst being close in total variation distance. So for Brownian motion, the Cameron-Martin theorem tells you that you can add a drift to Brownian motion, and if the drift is small enough, you're close, but you can't add arbitrary functions. You can only add functions that are in the Sobolev space H1. So the function that you add has to be in L2, and its derivative has to be in L2. But if you do that, then you can shift. So if you want the constant function to be an allowed shift, well, then you better have an atom at 0 in the spectral measure. So you really need constant functions to be in your Hilbert space. And that's it's a condition that's too strong. You don't want to work with such a condition. So yeah, this is really not true literally. So what we need to do is find some sort of approximate version of this. We want to understand how close can we approximate a constant function in such a way that the field and the shift is close in total variation distance. And yeah, what we're able to do is do this in a way that's useful. Okay, so let's understand how to do this shift. Okay, and we'll do it first for the Bargmann-Fock. It works differently for the Bargmann-Fock field and for the random plane wave. And really, this is the origin of the difference in order of variances. The fact you get r squared for Bargmann-Fock and r cubed for random plane wave come down to ultimately how large your epsilon can be in this shifting operation. How much entropy there is in the field that allows you to make these level shifts. Okay, so the proof is going to go via 3 kind of more or less standard facts, but yeah, since there might be non-experts in the audience, let's make these facts explicit. So what we first observed is this, Dimitri mentioned this moving average representation. So if we assume the covariance kernel is integrable, and the Bargmann-Fock field, this is true because the covariance kernel is Gaussian, so it's certainly integrable, then you can have this very useful representation of a Gaussian field as a stationary moving average. So in particular, there exists some kernel Q, some smoothing kernel, such that if you smooth your white noise by the smoothing kernel, in particular you convolute them, then you're left with the field. And how do you find this kernel? Well, the only property it needs to satisfy is that its self-convolution should be the covariance kernel. And you can find this using some Fourier analysis. So you go to the Fourier domain, you take a square root, and then you go back to the spatial domain, and that finds your Q. Because of course, convolution, Fourier transform takes convolution to multiplication. So yeah, by going to the spectral measure, by taking a square root and going back, you get your Q. Okay, and this is extremely useful representation, really. But as Dimitri said, the random plane wave does not have such a representation because its covariance kernel is not in L1, and more precisely, it's because there's no spectral density. The spectral measure is singular. Okay, so we have this spatial average, this moving average representation. What can we do with it? Well, we can chop up our white noise into boxes and then orthogonally decompose the white noise in each box. So this fact 2 says that if I have my white noise and I restrict it to a compact domain, any compact domain, and then I convolute with my smoothing kernel, this gives me some Gaussian field on the plane, but it's not stationary anymore because you're not convoluting with the whole white noise, you're just convoluting with some small patch of white noise. But anyway, it's a Gaussian field on the plane. And it has an orthogonal decomposition in the sense that Dimitri talked about at the start of his talk. And it's a very nice one. So what you do is you sum up IID Gaussians, and the basis functions are nothing more than the convolution of this smoothing kernel with any orthonormal basis of L2 on the compact domain you're working on. So you have to think that white noise is the canonical noise in the L2 space. So by decomposing L2 orthogonally, that's going to yield a orthogonal decomposition of the field. And it's actually very simple to prove such a result. It's just Parseval's identity, really. Okay. So why is this useful? Because the idea is that we want to pick as our orthonormal basis we want the constant function to be one of our orthonormal basis elements. And that's going to allow us to shift by a constant function. Okay, so the third fact is now, well, how do I shift standard Gaussian vectors by some amount to make sure they're close in tertiation distance? So if I have a n-dimensional Gaussian vector and I shift it by epsilon, then it's very simple to see that the tertiation distance is small if and only if epsilon is smaller than 1 over root n. So you can only shift by 1 over the square root of the dimension of your Gaussian vector in order to make sure that the laws are not too different. And the proof is really quite simple. There's Pinsker's inequality, the most useful inequality when you're working with the tertiation distance. Is that it's bound by the square root of the relative entropy. I'm not going to define these things. If you're not familiar with them, then yeah, you'll have to take it as given. But for those that are, it's bound above by the relative entropy of the measures, and relative entropy is additive over product measures. So you get immediately the dimension square roots here coming out of the bounds. That's where the square root n comes from. The fact that relative entropy is additive for product measures. Yes, okay. So let's put everything together to prove what we want to prove. So putting these three facts together, we get the following result, that if I take the Bargmann-Fock field, restrict it to the ball of radius r, then I'm allowed to shift it by this function that's approximately constant. So what is this function g that I'm shifting by? Well, it's the convolution of q with, sorry, this should say the identity, function on the ball, sorry. So the constant function on the ball, convoluted with q, restricted to the smaller ball. And because q is decaying rapidly, this thing is almost a constant function on the ball of radius r. And the constant of proportionality is just the integral of Q. Okay, so this looks a bit complicated, but the upshot is that there exists some function that's almost a constant function on the ball, such that I can shift my field by it. And that's going to be close in toleration distance if and only if the shift is less than 1 over r. So the key thing to observe is that this quantity is small if and only if epsilon is smaller than 1 over r. So in words, it says that I can shift a Gaussian field by at most 1 over r in order to stay close in toleration distance. I cannot shift it by more than that, but I can shift by 1 over r. Yeah, that's the take-home message. As I said, it's not literally true because I can't shift by constant functions, but I can shift by something that's almost constant, very close to being constant. And to prove this, well, you just chop up your white noise into boxes, decompose each white noise orthogonally using this constant function on the box, and then use the the shift of the IID Gaussians to get the result. Okay, so yeah, the upshot is that as long as this integral of Q is not 0, then I can shift by 1 over r for my fields. And this condition is, so how to understand this condition? Well, it's the same condition Dimitri mentioned, which is that the spectral density should be non-zero at the origin. Let's just understand that because we're assuming the covariance kernel is in L1, the spectral density at the origin is so this is just Fourier analysis. So it takes the Fourier transform takes the integral of Q to the value at 0 of its Fourier transform, and the value at 0 is the square root of the spectral density at 0. So yeah, this condition is really equivalent to what Dimitri mentioned, that the spectral density should be not 0 at the origin. Okay, and in particular, it's true for the Bugman-Fock field. Good, so this is quite a useful fact. I mean, it might be useful for other people working on Gaussian fields, that you're really allowed to shift Gaussian fields by 1 over r without changing the law at all, or a very small amount. Okay. Good. Are there any questions about this?
May I ask one?
Yes.
Stephen? So if you go back to the expansion that you wrote for the Bugman-Fock, the series expansion, you can...
oh, sorry, I'm annotating, yeah.
So that can be done for any Gaussian process. That's like the Carhian and Lev expansion, right? What you have, is that right?
So yeah, every Gaussian field has an orthonormal expansion just by orthogonally decomposing the Hilbert space associated to it. The Kalman-Love expansion is a special case of that, where you take eigenfunctions of the covariance operator.
So what is it about the Bugman-Fock that is special here? This that it is of the form Q star something? Is that important?
Yes, exactly. That it has a white noise decomposition. So this is only true if the spectral measure is absolutely continuous with respect to Lebesgue. So it needs to have spectral density.
Okay, but is that in the next slide? Because there was an n in the Gaussian vector, and that n has to be chosen, right? So that is somehow the...
So this n is the number of boxes. What I've done is chop the plane into unit boxes. And so there's r squared unit boxes that is going to cover my ball of radius r. Yeah, so where does the r, it's a good point, where does the r come from? It comes from the fact that I have chopped the domain into r squared unit boxes.
Okay. Okay.
Yeah. I mean, you could chop it into larger boxes, but then your constant function has to be L2 normalized. So you end up with a constant that gets worse and worse. Yeah, you really want to be chopping into unit boxes.
Okay.
Yeah, and shifting by the constant vector the constant function in each box. Yeah, so you're just using the entropy of the white noise. You're saying that in the white noise breathes as well. So the white noise can go up and down It has entropy in terms of like constant shifts. Okay, so let's do the same thing for the random plane wave, or well, okay, for the random plane wave, the argument doesn't work because we don't have this moving average representation. So the random plane wave is a more complicated field to study, really. And there's a good reason for this because, yeah, the Hilbert space associated to the random plane wave, it has wave-like functions in it. So it's got solutions of the Helmholtz equation. That's what the Hilbert space consists of. So there are no constant functions in this, apart from the zero constant function in this space. And there's not even any approximations of them. So there's nothing that looks approximately constant in the random plane wave. You'll never see a realization of the random plane wave that looks constant on a large area. So you cannot expect you be able to shift by something that's approximately constant. Okay, so what do we do? Well, we need to do something a little bit different. So this is what we do for the random plane wave. We use a different orthogonal decomposition of the random plane wave that Dimitri mentioned in terms of IID Gaussians, sine and trigonometric polynomials, and Bessel functions. So this is kind of a decomposition in the spectral domain rather than in the spatial domain, which makes it a little bit different. But anyway, so the nice thing about this decomposition is that you can truncate it after a small number of terms in order to get something very close to the random plane wave. So yeah, the point is that the Bessel functions start to decay really fast as soon as the order of the Bessel function is larger than the argument of the Bessel function. And yeah, if the order is larger than the argument, this thing is exponentially small. So in this orthonormal decomposition of the random plane wave, I only need R terms, or more precisely 2 times R terms, in order to approximate the random plane wave on a ball of radius R. So that's really different to a generic field. For a generic field, if you want to approximate it on a ball of radius R, you should have R squared bits of randomness in order to approximate it, because it's kind of looks different on every unit patch. So you need R squared bits of randomness to define it. But for the random plane wave, that's not true. You only need R bits of randomness to define the field or approximate the field on a ball of radius R. So this is really the fundamental difference between the random plane wave and generic fields, is this kind of degeneracy, that you need less randomness to define it or to approximate it. Okay, so for the random plane wave, we don't want to shift our Gaussians by a fixed amount. We want to multiply them by something that's close to 1. But nevertheless, we have the same kind of result, that if you have a standard Gaussian vector, you can shift by epsilon, but you can also multiply by 1 plus epsilon. And the tertiation distance is of the same order, epsilon square root dimension. And once again, this is just Pinska's inequality. And then you just compute the relative entropy precisely. Okay, so yeah, we're gonna shift the standard Gaussians in the expansion, or we're gonna multiply them by 1 plus something small in order to modify the field. So what do we do? Okay, we fixed a level that's not 0. And here we'll see why we have to exclude level 0 for the random plane wave. Because in the statement of the results, one of the differences between the Bargmann-Fock field and the random plane wave was that we had to exclude level 0. And yeah, so this is where it comes into play. So what we do is we say, because if I work with the truncation of the field, where I truncate after 2 R steps, then I just have I can view the field as living in a standard Gaussian space with dimension 2R. And so I can multiply that by this constant L plus some small epsilon divided by L. And that's going to be close in total distance as long as my epsilon is smaller than 1 over square root r. So why square root r? Because the dimension is only r. Remember, we could truncate after 2r steps. The dimension is only 2r. It's not r squared. So in this argument, we had the square root of the dimension. The square root of the dimension is now square root r. So I can shift by this much larger amount. Shift in this multiplicative sense. So what we see is that as long as L is not 0, I can compare the number of level sets at level L with level L plus epsilon, as long as epsilon is smaller than 1 over square root r. So for the random plane wave, it's not that the whole field breathes, because it's not true that you have these level shifts, but nevertheless, the number of level set components does stay close when you shift the level. It doesn't change too much in total variation distance. Okay. Yeah, so what's kind of subtle about these arguments is that here we're not using critical points we're not using Morse theory. We're not saying that the number of components it doesn't change much when you change the level. We say that the law of the total variation of the connected components doesn't change much. So this is a very different type of statement. It's controlling the respective laws of these things. I mean, the number of components might change a lot when you realize them and shift the levels, but the law hasn't changed much. Okay. So let's just sum up what we've done. We've said that for the Bargmann-Fock field, I can shift by 1 over r to get laws that are close in total variation distance, whereas for random plane wave, I shift by this much, much larger amount, 1 over square root r. Okay. Good, and yeah, as I mentioned, this is really due to the degeneracies in the random plane wave. I mean, how to think of this degeneracy? Well, you can think of the spectral measure being supported on a one-dimensional subset of R2. So the spectral measure lives on the unit circle. It's a degenerate spectral measure. So this is really what's driving this, this degeneracy. That's one way to think about this degeneracy. But I prefer to view it as like being able to truncate this orthonormal series after very few terms. Okay, so let's turn to the third idea, and it's not really our idea, it's due to Chatterjee, but it's a very, very nice idea, and could be useful for a lot of different things. So if you'd kind of switched off, you can switch back on, because potentially this could help you work on your own problems or help a lot of people. So I want to promote this idea, and yeah, it's from a couple of years ago, and Chatterjee proves this very simple lemma. I mean, the proof is like 3 or 4 lines. And what he says is that if you have 2 random variables, then the probability that one random variable lies in some window is small if the total variation distance between x and this other thing is small, and if the probability that when you realize both of these variables, that the difference the difference is likely to be small as well, with high probability. So it says that a random variable is not concentrated if you can couple it to another random variable in such a way that they are different with high probability. So applied to a sequence, we want to apply this to a sequence of random variables. If you want to prove a lower bound on the variance of any sequence, just as complete general setup, you want to prove a variance lower bound, it suffices to find another sequence such that you can couple them so that they're close in total variation distance, and such that when you can put them on the same probability space in a way that they differ by that fluctuation scale. And if you can do that, then you immediately deduce a variance lower bound via this coupling method. So yeah, this idea, I mean, Chatterjee was the first to really abstract it out in this way, but it had been used in an ad hoc way in certain select problems to prove lower bounds on variance. Because there aren't that many tools to prove lower bounds on variance. I mean, you have like the second moment method, you have some coupling methods, and then ad hoc methods. But yeah, Chatterjee was the first to realize that this is some very general technique that applies to a lot of different problems. It's very, very powerful. Okay. yeah, so we were lucky we knew about this method, and we realized it applied to this problem to give this result. Okay, so let's put everything together. So what we do is we fix a level, and we fix a certain shift of the level that's going to go to 0 with the scale. And then we compare, so let me try and clear my drawing, okay. Okay, so we compare the number of connected components at the level with the number at the shifted level. These are our two sequences. And we know that these things converge in a law of large numbers sense to their densities. So what that means is that if this density is not a critical point, if this level is not a critical point of the density, then the expected difference between these quantities should be of the order level change times volume times derivative, right? Because this is the density of the number of critical points. So if I want to know, at least in a first moment sense, how it changes when I shift the level a small amount, I have a kind of Taylor expansion that this is equal to the level shift, the volume, and the derivative up to smaller terms. Yeah, this doesn't come directly from Nazareth-Sodin's result. You have to do a little bit more control of the error, but at least intuitively, it's clear that as long as you're not sitting at a critical point of the density function, when you shift the level, you should pick up a large change in first moment. Okay. Good, so we have this is part of what Chatterjee needs in his result. We have a large change in the first moment. We want to use the second moment method to, remember in Chatterjee's result, it's not enough to have this thing large in expectation. We need it to be large in a probabilistic sense. So we need a bit more than just a first moment change. We need a second moment change. So here we bring in our...
May I ask a question, Stephen?
Yeah, of course, yeah.
So what is the coupling of X and Y? You are taking it in the same field, is it?
Yeah, exactly. The natural coupling, the totally natural coupling, where you are literally changing the level. Yeah. Yeah, so that's what's nice about this, the Chatterjee's method applied in this setting, that you have a very natural coupling of the number of level sets in different levels by realizing the field and then changing the level. It's the most natural coupling you could think of. And happily, with that natural coupling, it's easy to control the first moment and the second moment, because we have our Morse theory lemma that tells us that the second moment doesn't change very much when I change levels. This was the first idea. So we have the second moment method, Paley-Zygmunt inequality, that tells us if I have a control of the first moment and control of the second moment, I can leverage that into a high probability statement. I can say that actually these two random variables do differ by the correct scale with non-negligible probability. But yeah, it's crucial you have the second moment control as well in order to get such a statement. And well, then we're done, because we know for Bugman-Fock we can shift the level by 1 over r to stay close in toleration distance. So the coupling method tells us that the variance is the level shift times r squared squared. And this, because epsilon is 1 over r, this works out to be r squared. Whereas for the random plane wave, things are a bit different, because I can shift by more. I can shift by a lot more to stay close in toleration distance. So this exact same argument now yields something better. It yields epsilon r squared squared, which is now r cubed and not r squared. So how to understand this difference between r squared and r cubed? It's coming from how much can I shift the level in order to stay close in toleration distance. And because of the degeneracies in the random plane wave, I can shift by a lot more for the random plane wave in order to stay close. Okay. Good. So that's yeah, that's the end of the proof of the results. Before I talk about validating the conditions, are there any further questions? It's a good time to pause.
Stefan,
yeah.
One question. So for the second moment bound and so on, you use this lemma you stated at the beginning that the number of critical points between two levels is bounded, the number of components is bounded by the number of this lemma, right?
Yes, yes.
And this is the only thing in some sense specific to you're counting the number of level sets or excursion sets in the argument, in the sense that you need some variant of this. If you take any other functional, that if you had to take some other Betti number, then this is the analog one needs.
Yeah, exactly. Well, for any Betti number, I mean, this statement is still true.
With a certain index.
Yeah, but this is kind of the weakest
okay,
version.
okay, yeah, right. Okay, yeah, you're right.
And in fact, this is all you need. So the exact same argument really does generalize to Betti numbers.
Okay, great.
Yeah, it's because once you've kind of gone to a small enough window, yeah, you no longer care about the index or anything.
Yeah.
You can just throw away all topological information, just go to the critical point.
Okay.
Because you're working in a small window, it's enough to do that. Yeah.
Okay. Thanks.
Yeah, thanks. That's a good question. Okay. Good. So let me just mention in the last couple of minutes, how we can go about validating this condition. So as we saw, this argument, let's highlight where it appears. We really need the derivative to be non-zero, because if the derivative is zero, we don't get a large change when I change levels in first moment. And if I have to pass to the next term in the Taylor expansion, the second moment method fails because my second moment is too large now. So it's not like you get a weaker result. You really get no results at all using this method, at least as far as we can tell. So yeah, we really need this not to be at a critical point. Okay, so how can we validate this? Well, we go back to what Dimitri was talking about, that we can represent this density functional as a integral over critical points of different indexes. And so to remind you, M plus is the density of local maxima, and S minus is the density of lower connected saddles. So it's not just a local quantity anymore, it's saddles that have been partitioned into their topological type, lower or upper connected. And it's going to be more useful for us to write it as follows. So I'm going to say that the density of lower connected saddles is just the density of all saddles multiplied by the probability that a given saddle is lower connected. So if I take the field and I condition the field at the origin to have a saddle, and I force the saddle to be at height L, then I can just ask for the probability that that saddle is lower connected. And that's what this G function is going to represent. Okay, so using this, we can see that the only way that this derivative is going to be zero is that if this probability of being lower connected is exactly equal to this ratio of local maxima to saddles. And this right-hand side is explicitly computable, being local. So yeah, you can understand everything in terms of this probability of being lower connected. If you can understand this probability of being lower connected saddle, given that you are a saddle, if you can understand that, you can understand everything to do with this, this density function, and you know when it's critical. Okay, but this is a very difficult quantity to study, actually. The probability is lower connected. It really depends on the whole field, properties of the whole field. So are we in a better place? Well, we're in a little bit of a better place because we can make the following intuitive observation, that what should be true of this probability that it's lower connected? Well, it should be increasing, really, if you think about it. If you have a saddle at a higher point, then most of the field around it is going to be lower than the level. So it should be more likely that you connect below the level. Okay, maybe it's not very convincing, but at least intuitively you can see, you could hope that this function is increasing. And if it's increasing, you can hope to be able to prove it. So this was kind of our starting point. We thought about this, we thought, oh, it could be true. And actually, we can prove it. But interestingly, it's very hard to prove in general. We can't prove it in general. But happily, for both the Bargmann-Fock field and the random plane wave, we can prove it. But we use very specific properties of these fields. We use really explicit properties of the covariance kernel to do this. We don't have any soft argument. which maybe suggests it's false sometimes. I don't know. We don't really have a good understanding. But yeah, we can prove it's strictly increasing for both Bargmann-Fock and for random plane wave. Okay, so that's useful because we know what this probability is at the 0 level. At the 0 level, the field is totally symmetric. So the probability that's upper connected is the same as the probability that's lower connected. So it's a half. And so what we get is this kind of soft property that at positive levels, this probability is bigger than a half, and at negative levels, it's less than a half. And it's not, yeah, that's not such a strong statement, but it's all we have, and it's already useful to control this critical point, because it gives us regions at which this thing is not, this equality is not true. The right-hand side, as I said, is explicitly computable. So by comparing it against a half, we can really deduce our regions at which this critical point is not 0. And well, maybe 2 more observations and then I'll stop. Yeah, so for the Bargmann-Fock field, we additionally know that it's continuous. So we can go a little bit to the left of 0 while staying close, the probability being close to a half. So that allows us to extend our control a little bit to the left of 0. But for the random plane wave, you have something much, much better, that actually there are no local maximums at negative levels. The random plane wave satisfies the wave equation, and solutions of the wave equation only have local maximum at positive levels. So in fact, we know that this derivative is positive at all negative levels. Okay, and well, that leads to the result I mentioned before, to give our explicit control over the to validate the conditions. So I should stop. Let me just put up on the screen some questions. Yeah, and then I'll stop. Okay. Oh, maybe I'll say something. Okay, maybe, can I have another 2 minutes?
Yeah, please go ahead. You have a lot of time.
Okay, okay. So let me go through these questions. I mean, we've already covered most of them. As Dimitri said, it'd be really nice to know how many critical points these density functions have. We think that they're unimodal or bimodal, but we don't even know that the measure of critical points is 0. So what could happen is that there's a whole positive measure set at which it's constant. We can't even rule that out, for instance, because these things are really hard to get a grip on. Something we're really, really interested in is what happens when these conditions are not true. What happens when you add a critical point? Is the variance of smaller order, or is it still of the same order? And what we think happens, as I mentioned before, is that for Bargmann-Fock, this condition doesn't matter, and you always have linear variance. But for a random plane wave, what might happen, by analogy with the so-called Berry cancellation for the length of nodal set, is that you have smaller variance at certain levels. So it might be true that at critical points, or maybe only at level 0, we don't really know, it might be true that you have Berry cancellation, which would be very, very interesting to try and understand. And yeah, we don't really have a guess even of how small the variance would be in those cases. It's probably r squared log r or something like that, but we don't know. It's just a guess, really. And then, as Dimitri said, we're kind of working on matching upper bounds, and it would be nice to prove a CLT, but it seems quite challenging, actually. Okay, and the talk was based on, yeah, Dimitri's talk as well was based on these works, which you can have a look at if you're interested for more details. Okay, thanks a lot.
Okay, we can take some questions, if any. Are there any questions?
Can I ask a question?
Of course.
Yeah, go ahead.
Yeah. So, Stefan, sorry to bother again about that lemma on the difference between the two bound in terms of the critical points. I want to understand, okay, so this is again, I mean, the need to say a separate lemma like this or prove is like what Dimitri pointed out, that because you are dealing with a compact manifold with a boundary. Because I thought there is a Morse theory in general gives this.
No, okay, so maybe I should be more explicit. What I'm crediting to myself here is not this first statement, it's this second statement.
Okay.
Yeah, this first statement is purely Morse theory.
Okay.
This is quite simple. It's how you, and also the Kac-Rice formula is simple, but there's a little bit of technical work to prove that this thing doesn't blow up.
I was a bit, I was somehow thinking even the first, there is something I missed in the first statement, some subtle issue I missed, I thought.
No, it's just Morse theory, yeah.
Okay, thanks.
Yeah, what's subtle is controlling this quantity and making sure it doesn't blow up on the diagonals, for instance. Yeah, it's a bit of work to do that.
Thanks.